Hello everyone, welcome to the NPTEL live problem solving sessions for the course Intro Introduction to Semiconductor Devices. We will start in 2 minutes. Welcome to Hello everyone, good evening. Welcome to first week of the course Introduction to Semiconductor Devices by Professor Naresh Naresh Kumar Imani from IIT Bombay. The course ID for this course is NOC 25E92. Uh, and my name is Mayank Goyal. I am a research scholar at the Department of Electrical Engineering, IIT Bombay. So this is a 12-week course being taught by Professor Naresh Kumar Imani, who is an associate professor in the Department of Electrical Engineering, IIT Hyderabad. The course plan for this week is introduction to semiconductors and quantum mechanics. So the properties and how the energy levels and energy bands are formed, band gaps, and how to classify electrons, holes, effective mass. So this is a problem solving tutorial session that will be held every Sunday 6 p.m. to 8 p.m. at this Google Meet link. So first we will do a recap of the lecture using the slides provided by the professor. So this is a quick review of the this week's lectures. So these are some basic values that you need to remember for semiconductor purposes, such as Planck constant, h equals to 6.6 into 10 raised to minus 34 joules per second, light velocity c equals to 3 into 10 raised to power 8 meter per second, electron rest mass m is not 9.1 into 10 raised to minus 31 kilograms, electron charge q equals to 1.6 10 to the power minus 19 coulombs. Now this is a electron volt unit, which is basically how much how much voltage needs to be applied. So how much energy needs to be applied to give this charge a 1 volt of potential, that is 1 EV, that is 1.6 into 10 to the power 19 joules. De Broglie, and then this is quantum mechanics, very important formula for quantum mechanics, which is de Broglie equation, which relates wavelengths to particle like momentum, lambda equals to h by p. Then this electron energy is then using this formula, the electron energy is calculated using E equals to p square by 2m naught, and the photon is equals to h nu or h by lambda or pc, momentum into velocity. So this is an example that is given, that if we have a photon of wavelength 1.24 micron, then it and the energy it has is 1.6 into 10 to the power minus 19 joules. However, joule is not a convenient unit of energy, so instead we refer in terms of EV, and this relationship is given as EV equals to J by Q. So to calculate EV, you just have to divide the joules value by charge value, which is 1.6, which is 1.6 10 to the power 19 coulombs. So 1.6 into 10 to the power minus 19 joules will be equal to 1 electron volts. And using this formula, equals to hc by lambda, if you calculate your lambda, it will come out to be 1.24 microns. So this value you can directly use to convert between electron volts and wavelengths. You just have to divide by 1.24 and you will get the value in wavelength value in microns. Now this is a 1D potential box equation where the particle is trapped in an infinite potential well of width L, and so the particle is an electron of mass m and is moving with the momentum p. So so its energy conservation is given in the form of Schrodinger equation, which is kinetic energy plus potential energy total energy. So kinetic energy is given by minus h cross square by 2m del square psi by del x square. The potential energy is given by V of x psi x, and the total energy is given by E. So this is E psi x. So psi x is the particle wave equation of the electron, and then it also satisfies the equation E psi x equals to I h cross del psi by del t. So it's an infinite potential well, that is inside there is zero potential energy, and outside the well it is infinite potential energy. And so the particle is trapped inside this. It cannot go outside because it cannot go into the region of infinite potential energy. Because if there's infinite potential energy, then the kinetic energy will have to be zero to conserve energy, total energy. Assume so we assume that there are n number of states allowed inside the well, energy states, and so you will find that each of the energy at each of the state is quantized, and we can calculate by using the formula En equals to p square by 2m, which is equal to h cross square k square by 2m. And then if we put the values for h k, we get n square h square by 8m l square. So you can calculate the difference between two energy levels, ef minus ei equals to h nu h c by lambda, which is, you just put the values here, nf square minus ni square h square by 8m l square. And if you have a, instead of one dimension, you have a two-dimensional box, then the energy is En is given by p square by 2m h square kx square plus ky square by 2m, and then you open it, you will get nx square by lx square plus ny square by, ly square h, h square by 8m. And then you can calculate the probability of finding a particle using the, for that we using the wave function. So if the wave function is given by psi x, the probability of finding the particle is given by square of psi x. So at particular x, the probability will be p of x equals to integration of mod of psi x square dx, and the total probability, if we consider all the points, then when the probability is added up, it should be 1. That is basic formula for probability. So that is given by, so basically if you sum over all values, then the total probability come out to be 1. And so the probability changes at a particular position and a particular energy level. So which differs from classical energy, where probability is independent of energy. Now this, if we take a finite well instead of an infinite potential well, where the region in outside regions there is zero energy, and there is a region 2 which has a v naught energy. So the particle will come from here, it will lose energy in this region, and then it will go out again. So this is called tunneling. In classical mechanics, the particle will rebound from here, but in quantum mechanics, the particle tunnels through this barrier if it has enough energy, and that is given by this formula. The probability of transmitting through this region is given by t equals to 16 e by v naught 1 minus e by v naught exponential of minus 2 kappa a exponential minus 2 kappa a. So this formula you may not be using in this course, but it is given for your understanding, that the kappa is square root of 2m v naught minus e by h cross square equals to 1 by eta, and eta is the penetration depth that it can go into the into the barrier region. So now so these are the initial values that you have, initial points that you have to remember for this course. Now let's move on to the recap of the lectures. So first, what is semiconductors? Are basically materials whose conductivity can be modified from a highly conductive to a highly resistive state. So there are three type of materials: insulators, semiconductors, and metals. So metals are highly conductive, insulators are highly resistive, and semiconductors have conduct can have their conductivity modified between modified. So this is the range of modification that can happen. So some popular semiconductors are silicon, germanium, gallium arsenide, cadmium sulfide. So you can see for silicon, the conductivity can be modified from 10 raised to power 3 Simons to Simons per centimeter to 10 raised to power minus 5 Simons per centimeter. For gallium arsenide, this is even higher. It can go from 10 raised to minus 8 to 10 raised to power 4. So generally, the materials from group 3, 4, and 5 show semiconducting nature. So group 4 generally show elemental semiconducting nature like silicon and germanium, and we can also combine multiple materials to form compound semiconductors, which are generally made from group combining one element from group 3 to one element of group 5, such as gallium arsenide, indium phosphide, indium arsenide, and then also from group 2 and group 6 can be formed like cadmium selenide. And then you can have multi, more than two also, like indium aluminum arsenide. So classical classical and quantum mechanical description of motion. In classical mechanics, the motion is described as by deterministic variables like position, velocity, and energy. Whereas in quantum mechanics, the motion is described by a complex wave function psi of x comma t, which in a simple, so this is one example: sine of kx e power iota omega t. This is just one example of a wave function. In classical mechanics, the outcomes are predictable, where in quantum mechanics the outcomes are probabilistic. And so classical mechanics is mainly used to describe the macroscopic world, whereas for microscopic world, where we reach the de Broglie wavelength scale, we use quantum mechanics. So de Broglie hypothesized that materials can exhibit both particle-like and wave-like nature, and gave the formula lambda equals to h by p. To we have studied this, and so if if an electron is moving in a circle, then it will have a particular energy which is quantized, and it is explained by quantum mechanics. So we can calculate the so it won't be moving in a straight line. It will have a wave like nature, and the the formula for that is 2 pi r equals to n lambda, where n is an integer. So this is a example where you are calculating the de Broglie wavelength of an electron traveling at a velocity of 10 raised to the power 5 meters per second. So first you calculate the momentum of this particle. So we know the momentum is given by mass into velocity. We know the mass of an rest mass of an electron is 9.1 into 10 to the minus 31, and velocity is given by 10 to the power 5. So you can multiply it, you will get 9.1 into 10 to the minus 26 kg per meter second. So now you calculate h by p, which is 6.63 into 10 to the minus 22 divided by 9.1 into 10 to the minus 26, and that comes out to be 7.3 into 10 to the minus 9 meters. So now you can convert it into nanometers, so that will come out to be 7.3 nanometers. So the wavelength comes out to be 7.3 nanometers, and you can convert, you can also directly calculate from calculate using wave number, wave vector, which is k. So instead of lambda you will write instead of lambda you will write 2 pi by k. So if you calculate this, so h by 2 pi is called h bar, which is the reduced Planck's constant. So reduced Planck's constant is denoted by a bar over h, or h bar, and it is written as h by 2 pi, and then 2 pi by lambda is your wave vector k. So momentum can also be defined as h bar k. So now we come to Schrodinger equation. So this equation we have just seen. This is the kinetic energy part minus h cross square by 2m del square by del x square. Then this is the potential energy part, V of x, and the total energy is given by E, and you multiply it to psi of x, and the eigenvalues of this are give the wave vectors for each energy state. So this is called time independent Schrodinger equation because it does not involve time. So we assume that the particle state is not varying with time. It is constant in time. So and so we first calculate the free electron solution. So particle is said to be free when V of x is 0. So we put V of x equals to 0. So we get minus h square by 2m del square psi by del x square is equal to E psi of x. And you solve it. We assume we take a we take this on the left hand side, we multiply it all over. So we get the del square psi by del x square plus 2m e by h cross square psi equals to 0. We let this be equals to k square. So we get del square psi by del x square plus k square psi equals to 0. Then we assume then we assume psi of x equal to e power minus e power iota kx. This is first we are assuming, and then we put it here. So we take double differentiation of this. So we get ik ikx square psi plus k square psi of x equals to 0. And you can also, instead of iota kx, you can also take minus iota kx. So we and iota kx means cos of kx plus iota sine of kx. E power iota kx, this means is, so both of these you can see, both of these are valid solutions. So in the generalized forms we can write psi of x equals to a e power iota kx plus b power plus b e power minus iota kx. And if we open it in this form, we can write it as c sin kx plus d cos kx, where where we are assuming some constant value, where c and d will be some constants. And if we plot this, you will get, if we plot in E versus K, so we had taken K square equals to h 2m E by h cross square, so E will be h square K square by 2m, and we know E is equals to P square by 2m. So when you plot E versus K, so and we have also studied, so from this formula we get that P equals to H cross K. We have just also studied that. So when you plot this, you will get a parabola, and this is called dispersion relation. So this diagram is called EK diagram, energy versus momentum diagram, and this is a very important diagram for quantum mechanics, for studying energy bands. So the negative momentum value would mean that the particle is traveling in minus x direction, and the positive momentum will mean that a particle is moving in the plus x direction. So then this is infinite potential infinite potential well, which we have just studied in the beginning. So now, what if you have to calculate the psi of x? How can we calculate? We know that the wave function will be zero in the barrier regions because they have infinite potential. So the kinetic energy will be zero. So there won't be any particles here. So and so and we know that psi of x. So we know that psi of x has to be double differentiable. So it has to be continuous at the boundaries. So if psi of x is 0 here, then psi of x is 0 at the boundaries also. So psi of x is 0 in regions 1 and 3, and then psi of x is also 0 at values x equals to 0 and x equals to L. And for inner regions, we inner inside the second region the potential is 0, and for 0 potential we have calculated psi of x to be c sin kx plus d cos kx. Now we can put the boundary conditions on this, which is psi of x equal to 0 equals to 0 and psi of x equals to L equals to 0. So we will get that d is 0 for this. So psi of x will be c sin kx, and and when you put x equals to L here, you will get that c sin kl equals to 0. So kl must be equals to n pi. So k can be calculated as n pi by L. So you can see that for n varying 1, 2, 3, we can get the moment k values, since pi is a constant and L is known to us, which we have fixed the value of L. So we know from kn, then we can put this in the energy values, which is equal to h square k square by 2m. We put this h square 2m by h square by 2m into n square pi square by L square. So using this we can get the energy, and we can also get the psi of x, which is sin kx, which is sin n pi by L x. And then using both of these values, we can then plot the wave function as well as the energy in each region. So the wave function you can see for first level, for second level, third level, fourth level, and fifth level we have plotted. And this is the probability function psi and psi square. And the energies for first level would be 1, 5, some 11, some 19, some 31 approximately. And and you can also calculate from the dispersion relation, where for each k you get a particular e, e value, and you can see from here that it rises it does not rise linearly, it rises very fast for each increasing k value. So for quantum mechanical, the L has to be similar to lambda b. If it is greater than lambda b, then there is no need for using quantum mechanics. You can just use classical mechanics. And then this is Heisenberg uncertainty principle. Lambda x lambda p is greater than or equal to h bar by 2. So you can now solve this. Calculate the first three energy levels for an electron in an infinite potential well of width L equals to 1 nanometer. So you know this formula, En equals to h bar square k square by 2m, which is h bar square by 2m, n square pi square by L square. So L we know here is 1 nanometer. So you can, so if you calculate this, you solve all this, you will get approximately 10 to the minus 19 joules, and we know 1.6 into 10 to the minus 19 joules can be written as 1 eV. So you can convert this into eV values and then write E1, E2, E3 in terms of eV, and you will get something around 0.3 eV, then 0.2 eV, 3.5 eV, something like that you will get. You can solve this. So you can see then the difference between infinite potential well and finite potential well. So in infinite potential well, we assume that the potential in the barrier region is infinite. So for finite potential well, the barrier is not infinite. There is some finite potential in the barrier region. So we so there will be some tunneling in this region. So you can see for finite potential well, for each of these there is some tunneling tail in the barrier region, and you can also see the energy has been greatly reduced. So for so here the E5 is coming here. Here the sixth energy state is coming below the fifth energy state in the infinite potential well. So the energy has been reduced, but in the infinite potential well there are infinite many energy states. But in the finite potential well, the energy states will only be equal till the barrier height. After the barrier height, the electron is no longer trapped. So there won't be energy. There won't be any quantized energy states. So so this is then calculated using transmission probability. Now we come to 3D potential well. So an atom, we can consider that an atom is a 3D potential well, and that electrons are experiencing a spherically symmetric potential well, where the dependence is 1 by r. So we assume that the depth of potential is finite. So nucleus is at some finite depth, and we assume that vacuum is at zero potential, and that we assume that vacuum, that free state where the electron is no longer bound to the atom, that is that is ground state, that is zero energy state. So when the atom is bound to the so electron is bound to the atom, so it is experiencing some attractive potential from the nucleus. So we assume that it has some negative potential, and that has some depth, some fixed depth. It is not infinitely deep, and so it is radially confined, with each confinement given a quantum number n. And then to to quantize other symmetries, azimuthal and polar symmetries, we get additional quantum numbers L and M. where L can be 0, 1, 2, and so on, and M, and it goes up to n minus 1. L can go up to n minus 1, and M goes from minus L all the way to L. So using this, we get multiple energy levels in an atom. First, where you have n, so you have n equals to 1, L equals to 0, and M equals to 0, that is 1s. Then n equals to 2, L equals to 0, M equals to 0, that would be 2s. Then for n equals to 2 and L equals to 1, M can go from minus 1, 0, 1. So that is 2p, and there are 3 states. And and so by and so this is each energy state. And by Pauli's exclusion principle, we get that no two electrons can have all same quantum numbers. So we generally have four quantum numbers: n, L, M, and s, or sometimes it written as ms, which is given as spin quantum number. So an electron is a fermion, so it has two spin states, which is plus half and minus half. So each energy state can have a maximum for two electrons, one for plus half and one for minus half. And so this is how the energy states and orbitals are given. And so you can see how the energy changes. So 2s is lower at lower energy than 2p, then 3s, 3p, 3d, and 4s, 4p, 4d. So you can see 4s is almost the same energy level as 3d. So if we put silicon, which has 14 electrons, so it will first fill 1s, then 2s, then it will fill 2p, 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 then 3s, then 3p. So so 3p here it has shown two electrons here, but ideally what will happen is one electron will be here and one electron will be here, because that has a, that has a lower energy than putting both electrons in the same energy state. So it should be 1 and 1. And then this is Bohr model where Bohr model where the nucleus is sitting at the center, and then these are electron rings, electron shells. So this is 1s, this is K shell, L shell, and within each shell there are orbitals S, P, D, F. So then there are core shells, which is inner shells, and valence shells, which is the outer shell. So the outermost shell is called valence shell, and the innermost shell are called core shells. So first the inner shell will fill, then the electrons will fill the outer shell. So the core shells are fully filled and they are tightly held. So they do not contribute to conduction. Only the electrons in the valence shell, which are half filled and incompletely filled electrons, they contribute to conduction. So you can see for a silicon atom which has 14 electrons, so the configuration is given by Ne, which is neon. So neon so neon plus 3s2 3p2, so which is the third third energy shell. So you have eight states, uh, two states in one, 3s, and six states in 3p. So out of those, four have been filled and four are unfilled states. Now we come to lattice structure of silicon. So there are three types of lattices: crystalline, amorphous, and polycrystalline. So in crystalline, the electrons are arranged in a pattern, pattern with symmetric pattern, which follows some rules, and they are perfectly oriented. Whereas in amorphous, the electrons are oriented randomly. There is no orientation. They are randomly ordered. And then we have polycrystalline, where there are regions of crystallinity, which are also called domains. And so, but each of them will have short range order. So there will be some picometer, nanometer size domains of crystallinity. But each of the then individually the domains are randomly oriented. So it's a mix between crystalline and amorphous. So the silicon is, then again we come to silicon, which has the diamond lattice. So diamond lattice, the lattice that is in which the carbon atoms are arranged in a diamond. So for each silicon there will be four nearby atoms, four nearest neighbors, with lattice constant of 5.43 angstrom. So that is the difference between two two nearest atoms. And if you calculate the density, you will get 5 into 10 to the power 22 atoms per centimeter cube. And then we use Miller indices to define the orientation. So that crystal orientation, that is, if we cut a plane in the lattice, then what are the how the atoms are oriented, that is given by Miller indices. So this is a 2D visualization of the silicon lattice. So where each silicon is attached to four neighboring silicon atoms with a covalent bond. And now we come to chronic penny model, which gives the motion of electrons in a crystal lattice. So we assume that each lattice point is a potential well given by the nucleus, due to nucleus. So the well so the well will be like this, that we have studied now. And then we can the effective well will be like this. And then we approximate this curved states to rectangular barriers. So we assume that there are potential wells between, and then potential barriers, and this is a ordered structure. So we can take one small region, and then we can just repeat it multiple times. So we take this as 0, then we take the well length as A and the barrier length as B. So we get this structure, and this is periodically repeating. So here it will be minus A plus B, and this would then be A plus B, this point. And then we can solve for the motion of electron in this region. And then the spacing, how the spacing affects your electrons, that is given here. So at very large gaps, you will have equal energy, because you don't have the interaction between So if the barriers are very large, the interaction between atom in each lattice points is minimal. So you have, so all lattice points are equivalent. So you have same same energy, same wave function, same energy. So each, so you will have degenerate levels, which is the energies are same for each lattice point. And so if we assume there are n such potential wells, then there will be n such energy levels. But but if the d is less, then if d is less, then there will be interaction between neighboring potential wells, and that will result in two kinds of wave function. So their wave functions will then be connected, and that will result in two kinds of wave functions. One is symmetric wave function and one is anti-symmetric wave function. So symmetric wave function is symmetric around zero, and anti-symmetric wave function is opposite in positive and negative. So that is, for symmetric wave function, psi of x equals to psi of minus x, and for anti-symmetric wave function, psi of x equals to minus of psi of minus x. So you can then calculate this, and then delta E is given as the difference between the energy state level, energy of E of anti minus E of symmetric. So anti will always be at a higher energy level for, because it requires more energy to have anti-symmetric functions, and the closer, the lesser the d is, the more the energy difference will be. So you can see, if for non-interacting potential wells, which are basically far apart, you have delta equals to 0. You have n, if there are n wells, then there will be n degenerate energy levels. If for interacting potential wells where d is smaller, and the smaller it goes, the interaction increases, where you get delta E is given by E is anti minus E symmetric, and the delta E increases with decreasing D. So you don't have degenerate energy levels. So the degenerate is given in delta E, and you have multiple n levels. So for n number of levels, there will be n number of wave functions, and you will have n number of levels, which are all different energy values. So here you can visually see the difference, how the lattice spacing is affecting the energy levels. So you can see here, for D1, then you have a smaller energy level D2, so the energy increases slightly, and for D3 the energy increases even higher. And then you plot, if you take the chronic Penny model, and if you plot it in the EK diagram format, so you will have, from minus pi by to pi by, you will have like this. Then for if you go to the next level, then next energy state, you will have like this. So you basically, you have this, then you have this, then you have this. So for first level, you have energy states like this. For second level, the energy state goes like this. Third level, the energy state goes like this. and that you plot here, the first level energy state, then the second level energy state, then the third level energy state, then the fourth level energy state. But we know that the we know that the all the barriers are periodic in nature, so we can plot everything in the first potential well region. By applying periodic boundary conditions, we can shift this to here and then shift this to here. Similarly, shift this to here, shift this to here. So you can you can incorporate all the energy states in the between minus pi by to pi by region, and you can each of these, so near equals to 0, you can see that the energies energy E versus K is parabolic. Yes, you have raising your hand. You can speak or type in the chat. You want to say something, Pritika? So this minus pi by to pi by is called reduced K space, and it all the you can have all the energy levels in this state, and you can see there is some gap between the energy levels here, between each individual energy levels, and that is called forbidden energy gap. So there are no electron states in these levels. Please mute yourself. So this is then the formation of energy bands is seen as another way. So where if the so if the electrons are far away from each other, the atoms are far away. The atoms are far away from each other. That is like which is called such as gaseous state. So this is called gaseous state electrons. So there you have individual energy levels, atomic energy levels, which is given by 3s, 3p, and then as you come closer, there due to interaction between energy levels, you have broadening of you have separation of energy bands such that they mix into each other, and then they again start repelling, and you have at a naught, which is the lattice constant, you have a energy band. You have you have two kinds of energy levels. One is called valence band and one is called conduction band, and there's a gap in between which is called forbidden band gap. So each of the states uh, are separated into these, and the number of states are constant. So earlier also you had 8 states per atom. Now also you have 8 states per atom, and earlier you had 2 electrons in the 3s state and 2 electrons in the 3p state. Now Now all the electrons are in the bottom conduct valence shell, and there are no electrons currently in the conduction shell. So the valence shell is completely filled, and the conduction shell has 4n states which are all empty. So this is the summary we just studied. So that is how you get the energy gap due to the interaction between interaction between atoms in a lattice. Now, now from this we can have let's study electrons and holes. So so we when an electron goes from the valence band to the conduction band, it leaves behind a space for the electron. So that space for the electron is known as hole, or the vacancy that has been left is known as a hole. So since the since the movement of vacancy is dependent, so the vacancy, although the vacancy is on an atom, but the state of the vacancy is depending on the state of the electron. So the as the electron moves, the vacancy also moves in the same with the same wave function, but in the opposite direction, in the same wave function. So we assume the hole to have the same mass as the electron, but the but the we will see that the momentum is opposite. So the wave function is opposite. So to show that it does not have negative mass, we instead consider the opposite charge. So we consider that the hole has a positive charge equal to the charge of an electron. If electron is considered negatively charged, the hole is considered positively charged. Now the question is, does current flow in silicon at T equals to 0 Kelvin and T equals to 300 Kelvin? So we know that there are no so the conduction band is completely empty in the equilibrium condition, which is at T equals to 0. So if there are no electrons in the conduction band, there won't be any current flow. So at T equals to 0 Kelvin, there won't be any current flow. But T equals to 300 Kelvin, there will be some, due to thermal excitation, there will be some electrons that have gone from valence band to the conduction band. So there will be some amount of electrons in the conduction. There will be some amount of electrons in the conduction band which can contribute to the current flow. Therefore, there is current flow at equals to 300 K. So there are so so each so we call this electron and hole as a pair. We consider it as a pair, and it is called EHP, electron hole pair, and it can be generated through multiple processes such as thermal generation, where the the thermal energy is able to knock out is able to impart enough energy for holes to go to conduction go from valence to conduction band. Then there is optical absorption, the where the electrons can absorb energy from light and do the transition to the conduction band. Then there are other methods such as impact ionization and impact with high energy beams. Impact ionization basically means that at very high fields, the ions that are formed impart energy to the electrons, and so at very high energy field, the at very high when energy field or very high temperature, there are the atoms and electrons have enough energy that when they when they collide with each other, they release enough energy to get, to impart energy to other electrons to rise also. And also we can use do that with high energy. We can bombard the lattice with high energy beams to cause this impact. So probability of generation of electron hole pairs by thermal generation is given as proportional to exponential minus Eg by kT, where k is the Boltzmann constant. And for optical absorption, the rule is that for absorption, the energy of the photon should be greater than the energy of the band gap. And if the energy of the photon is less than the energy of the band gap, then the electron gets transmitted because there is not enough energy to overcome this barrier, the energy overcome this band gap. So there is no point of absorbing that energy. So that light photons uh, is then let being transmit without absorption. And so you can see for, and we had studied that to convert between energy and wavelength, we can use the formula 1.24 by lambda or 1.24 by ev. So for 500 nanometer photon, the corresponding band gap required would be corresponding energy required would be 2.48 ev. For telecom wavelengths, which is 1550 nanometer, it is 0.8 ev. And then an example for high energy beams is X-rays. So if you shine X-rays on, if I shine X-rays on this, then they have enough energy to provide electrons with very high energy that they can undergo multiple impacts with each other and have multiple electrons and give their energy to multiple electrons. So one each electron has enough energy to cause multiple electron hole pair generations by transferring the energy to other to to other electrons to break the bond. Now this forbidden energy gap is called band gap, and it is a characteristic of a material. So each material has a characteristic band gap. So for SiO2, the band gap is given as 8.9 electron volts. For diamond, it is given as 5.5 electron volts. So this is insulators which have large band gap. So there are very few possibility of having electrons in this EC region. Therefore, that is why they are very highly resistive. For metals, the Eg is very small, and in some conditions there is there is no Eg and there is overlap between conduction and valence bands. So so you have you have high concentration of electrons in the conduction band, and that is why they are highly conductive. And semiconductors have a moderate band gap, such as 1.12 ev for silicon, 0.66 ev for germanium, and 1.42 ev for gallium arsenide. Then that and this band gap is the cause of why a material is transparent or opaque. So if the band gap is much larger than the visible light band gap, visible light, so for glass which is SiO2, the band gap is 9 ev. So so and like the edge of visible light, let's say 300 nanometer, that itself is 3.7 eV. So it is even higher than that. So since the photo and all the visible light photons are have a lower energy than the band gap, so they all get transmitted and none of it is absorbed. That is why we can see through glass. But for silicon, the band gap is 1.12 eV. So so all the visible light is absorbed and reflected by the silicon. So we cannot see through silicon. Now there can be two types of band gaps. One is direct band gap, one is indirect band gap. So indirect band gap, so this is called top of the valence band and this is called bottom of the conduction band. So top of the valence band is the point in the valence band where the energy is maximum, and the bottom of the conduction band is where the energy is minimum. So if they are at the same k point, then it is called a direct band gap. And so when an electron goes from here to here, there is no energy is conserved. There is no momentum change, so energy is conserved, and there is high probability of energy of electron transition by absorption of energy. So ei plus h nu gives ef. There is no need for any other energy. And if the top of valence band and bottom of conduction band are not at the same energy levels, then it is called indirect band gap. And there, although there is a possibility of transition, but it requires a change of momentum, and this change of momentum is given by something called a phonon. So so it requires creation of a phonon, and so you need the energy from a photon as well as a phonon for transition, and that is why it is much less efficient. The probability is much lower. So this is the summary of what we have studied in this course this week. So now I will give you some practice questions, so that will help you for the assignments and the exams. First question is, according to de Broglie's hypothesis, all matter exhibits wave-like behavior. Among the following particles, which one will have the smallest wavelength associated with it for the same velocity? A. Proton, B. Electron, C. Alpha particle, D. Cricket ball. You can speak the answer or you can type in the chat.
Photon.
So the answer would be cricket ball, because it has the mass of cricket ball is much higher than all three of these, and we know that lambda b is equal to h by p. So for cricket ball, the p will be much higher, so lambda v will be much less, and which is why for macroscopic large objects, we the wave like behavior is much small, is much less pronounced, because the associated wavelength is so small that it is negligible. Consider an electron moving in a circular orbit around a nucleus. If the radius of orbit is halved, how does the de Broglie wavelength of the electron change? A remains the same, B halves, C doubles, D 4 times smaller.
4 times smaller.
That is incorrect. It will be half. So we had studied the formula is 2 pi r equals to n lambda b. So if r is halved, then lambda b is also halved. The wave function of a particle moving in free space. The wave function of a particle moving in free space is given by lam psi equals to e power iota kx plus 4 e power minus iota kx. The energy of the particle is A 3h square k square by 2m, B h square k square by 2m, C h square k square by m, 4 h square 5 h square k square by 2m.
H square k square divided by 2m.
The answer to this would be h square k square by 2m. So, so if you have to use this equation, e square psi by k, psi x square plus 2m h cross square in e psi equals to 0. You place the psi here, e power iota kx plus 4 e power minus iota kx. If you place it here and solve this, you will get E equals to h cross square k square by 2m. A silicon has a diamond cubic lattice structure with a lattice constant A equals to 5.43 angstrom, as shown in the figure below. The silicon crystal is formed by periodic repetition of the unit cells in x, y, and z direction. In each unit cell, 8 atoms at the corner are shared with 8 adjacent cells. Hence, the corner atoms are considered to contribute 1/8 of the unit cell. The 6 atoms in the center of each face are shared by 2 adjacent unit cells. Hence, they contribute 1/2 to the unit cell. Lastly, the 4 atoms within the body of the unit cell contribute fully. Hence, the effective number of atoms per unit cell is 1 by 8 into 8 plus 1 by 6 1 by 2 into 6 plus 4 into 1, that is 8 atoms. Determine the density of atoms in number of atoms per centimeter cube. So you can calculate it as number of atoms per unit cell divided by volume of unit cell. A 1.6 into 10 to the power 22, B 5 into 10 to the power 22, C 2.5 into 10 to the power 22, D 1 into 10 to the power 22. So the answer to this is 5 into 10 to the power 20. So you know A is 5.43 angstrom, which is 0.543 nanometer. So the volume will be A cube. So you calculate it, will come out to be 1.6 into 10 to the power minus 22 percent. centimeter cube, and the atoms we have there in the question per unit number of atoms per unit cell is 8. So just divide by 8 by 1.6 into 10 to the power minus 22, which comes out to be 5 into 10 to the power 22. So next question. Consider an electron confined in an infinite square well of width 1 nanometer. If an electron undergoes a transition from first excited state, which is n equals to 2, to the ground state, which is n equals to 1, it emits a photon. Calculate the wavelength of the photon emitted during the same transition. A 1.1 picometer, B 1.1 millimeter, C 1.1 nanometer, D 1.1 micron. So the answer to this would be D 1.1 micron. So you can calculate this from for so the energy is given as n square pi square h cross square by 2m l square. So L, if you put 1 nanometer, so and then pi square for n equals to 1, the energy is n pi square h cross square by 2m l square. So En is equal to n square E1. So E2 minus E1 will be 3 E1. So the the for the wavelength will be the change in the wavelength is equal will be equal to the change in energy, which is 3 E1. So E1 you can calculate by putting 1 nanometer, and we know, and we know that to calculate lambda you just have to do 1.24 by delta E, which you calculate delta in EV, you place it here, and you will get, so delta E will come out around 1.1 1.2 EV, and you place it here, the lambda you will get 1.1 micron. Next question. There are two semiconducting materials with energy band gaps EGA equals to 0.7 electron volts and EGB 1.4 electron volts. Which of the following is true regarding the probability P of I of electron hole pair generation at the same temperature? P of B equals to P of A, and both are not equal to 1. P of B is much larger than P of A. P of B is much smaller than P of A. P of B equals to P of A, and both are equal to 1. So the answer to this will be C. P of B is much less than P of A. So we know that probability is proportional to exponential minus Eg by kT. Since EGB is much larger, is greater than EGA, then exponential of minus Eg by kT will be much smaller for EGB. So PB is much smaller than PA. Next question. Consider two semiconductor materials, germanium with an energy band gap of 0.7 eV and sapphire with an energy bandgap of 9.9 eV. Which material will be transparent for visible light of wavelength lambda equals to 400 nanometer? Germanium, sapphire, both germanium and sapphire, neither germanium nor sapphire. So the answer to this will be sapphire, since so for 400 nanometer the photon energy will be 3.1 eV, which is larger than the germanium band gap. So germanium will absorb this photons, but it is much smaller than sapphire band gap of 9.9 eV. So sapphire will let it transmit. So it the sapphire will be transparent to the visible light, while germanium will absorb visible light. Identify which of the following statements is true from the given figure. Silicon is an indirect bandgap material and gallium arsenide is a direct bandgap material. Momentum is conserved in an indirect bandgap material. Silicon is a direct bandgap material and gallium arsenide is an indirect bandgap material. Momentum is conserved in a direct bandgap material. Option A, one is incorrect and two is correct. Option B, 2 and 4 are correct. Option C, 1 and 4 are correct. Option D, 3 is correct and 4 is incorrect. So the answer will be 1 and 4 are correct. So you can see from this you can see that silicon is an indirect band gap and gallium arsenide is a direct band gap, and the momentum is only conserved in a direct band gap material. For an indirect band gap material, the momentum is not conserved for transitions, and the additional momentum has to be provided using a phonon. Cutoff wavelength in micron for light that can be used for intrinsic excitation of semiconductor materials of bandgap 1.1 electron volts. A 0.85, B 1.125, C 1.45, D 2.25. So the answer to this would be 1.125. So the cutoff wavelength will be equal to the band gap of the material. So because any higher wavelength material will be transparent to the to, will be transparent to the material and will not result in excitation. So it can be calculated using the formula 1.24 by 1.1, which gives you 1.125 microns. The recoil momentum of an atom is Pa when it emits an infrared photon of wavelength 1500 nanometer, and it is Pb when it emits a photon of visible wavelength 500 nanometer. The ratio of Pa by Pb is given by 1, 1 by root 3, 1 by 3, and root 3. So the answer to this will be C, 1 by 3. So the momentum ratio can just be calculated from de Broglie wavelengths, which is lambda, Pa by Pb equals to lambda P by lambda A, which will be 1 by 3. So this is everything I had for today. Thank you for attending this session. You may ask any doubts you have. When atoms are arranged in a lattice, so and they are close to each other, then for n number of potential interacting potential wells, there are n number of wave functions formed. So there are n number of energy states for each level. There are n number of energy states for each level, and that is that is given as this level. So each of these contains n energy levels, and so so this is the number of energy levels between two adjacent atoms. So the where the gap is 0 to pi by a, then when you go for higher momentum, the energy level is pi by 2 pi by a, and for next energy levels, the energy from 2 pi by to 3 pi by a, this this is the energy level. So between each of these, there is some discontinuity, and this discontinuity is called forbidden energy band because there are no allowed energy states in this level. And so this is how it this is how the change in energy states occurs as atoms are brought from infinitely far into a lattice. So when they're infinitely far, the energy states is given by their normal atomic energy states, which is 3s and 3p, and each of the atom has experiences the same wave function. So all the energy states are degenerate. That is, they are the same for all atoms. But as they move in closer, there is interaction between the atoms, and the energy states start change number energy states start changing. So first they merge into each other to make a continuous energy band, and they again separate out as they come even closer to form two energy bands called valence band and conduction band. And there's a gap in between those energy states known as Eg, which is the band gap. So the class is completed, but if you have any doubts, you can ask. So here the wave function, we are given the wave function as e iota kx plus 4 e power iota k minus iota kx, and we are given that the particle is in free space, that is v equals to 0. So so we take the time independent Schrodinger equation h psi equals to e psi, and for v equals to 0 we know the state is del square del square psi by del x square plus 2m by h cross square e psi equals to 0. So then we replace psi with this equation. So we differentiate this equation, we get iota iota k square, we get k square, and here we have 2m by h cross e. So we have so here we just have k square outside. So this term will be k square psi, and this will be 2m by h cross square e psi. So we can then take psi separate and 0. So that then we solve it. So we get E equals to h cross square k square by 2m. So this term, when you put psi here and solve for this term, the answer you get minus k square psi, and then you can cancel out psi and solve for E in forms of k square. So you get E equals to h cross square k square by 2m, and that is your option, correct option. So the Schrodinger wave equation is given from the given from the energy conservation equation, where total energy is equal to kinetic energy plus potential energy. So the kinetic energy is given as equals to kinetic energy is given by as equals to h square by 2p h square by 2m p square by 2m, sorry. Kinetic energy is given as p square by 2m, and the p the operate the quantum mechanical operator for p is given as my h cross del by del x. So for p square, but so p square the operator, so the quantum mechanical operator for p square becomes minus h cross square del square by del x square, and v and then v of x is the potential energy at the position x. So we multiply it to the wave function, which gives the position of the particle at any given point. The position of the particle at a given point is given by the wave function. So we multiply the kinetic energy and potential energy plus potential energy to the wave function. So that should be equal to the total energy of the particle, which is E. So this should be equal to E of psi x. And this formula is called Schrodinger equation. Or this is in this one in particular is time independent Schrodinger equation, because we are assuming the state of the particles is not changing with time. Otherwise, then we'll have to incorporate time operator also, and the wave function will also be dependent on time. So electron hole pair basically means that when an electron go, so the valence band is completely filled. So when an electron goes from valence band to conduction band, it leaves behind a vacancy of an electron in the valence band. So that vacancy is attached to the atoms of the valence band. But it as the electron moves in the conduction band, the vacancy moves in the valence band in the same fashion, because the movement of vacancy is basically hopping of electron. So although vacancy is attached to at the nucleus of the atoms, it is behaves like an electron. Hence, we consider the mass of we consider the hole. We call this vacancy a hole, and we consider it to be like an electron, but with the opposite charge, because it is in the it is in the invert opposite parabolic region. So if we consider it same charge, the mass will come out to be negative, but mass cannot be negative. Hence, we'll consider it as opposite charged to one electron. So the hole sits in the valence band when there's an electron generation to the conduction band, and we call this electron and hole as an electron hole pair.
Okay.